So we have been concentrating on differential amplifier for the last couple of classes. But I mean, the overall idea of so we were looking into this differential amplifier with the whole purpose of embedding it into a negative feedback loop, because ultimately we want a high gain amplifier because we want to get a stable gain when we put it in negative feedback, right? So obviously by now you should understand the fact that even though we can get, let's say, in principle, infinite gain from this contraption theoretically, or very large gain, that gain is not fixed in terms of if we are trying to get a very good gain which is invariant of temperatures and ambient conditions, right? So we said that okay, so using negative feedback, probably we can get a steady gain, but the cost that we pay is we are not getting those very high values of gain that we can get from an open loop amplifier. By open loop amplifier, what I mean is, if we have this, let's say this is my GM. If I simply find out the input-output relation between this contraption, that is V0 over VE, it will be GM times R0, which in principle can be a large value. But in this case, in this case, V0 over VI, not V0 over VE, V0 over VI at best can be equal to K, where K definitely has to be much lesser than, this has to be much lesser than GM times R0, because it is only when the loop gain tends to infinity you get this. Okay, so that's a penalty. That's a penalty that you pay in negative feedback. That is, you throw away the gain that you are getting from a high gain amplifier. But the good thing about negative feedback is that you get very accurate gains, right? So the gains is invariant to ambient conditions. Not only that, if you connect a load, RL here, provided that the loop gain still is much more than unity, V0 over VI will be almost equal to K. However, if you connect a load directly in case of an open loop amplifier, the V0 over VE becomes directly proportional to RL. So if the load varies, your V0 varies. But if you embed that high gain amplifier in a negative feedback loop, even if the RL varies, the gain will not vary. So that's the whole purpose of doing all these things. Basically, we are after a very stable gain, right? So when you are using your electronic devices or any devices for that matter, you want a predictability in their performance. You don't want it to behave like something today and something tomorrow, or if the temperature changes or humidity changes and so on. So predictability, reliability is a very important aspect of any engineering system, and negative feedback helps us in achieving that. Now, one of the reasons this negative feedback works is you need high loop gain, right? You have a very good error amplifier which can kick the loop in the right direction in case it diverts from the direction of choice. So now naturally the thing that comes to our mind is there a range of RL? Is there a range of RL for which this loop will work properly, and for those in which the loop will not operate properly? So what do you think? Is there a range of RL or there is no range of RL? There is a range of RL. And what is that? What is that? How will you know what is the range? No, so this GM is, if you assume it's a diffam, this GM is GM by 2 for the diffam. This R0 is some RDS1 parallel RDS3 or something like that, right? RDS2 parallel RDS4, the stuff that we did yesterday. So that's what, do you need to draw the entire circuit? Or can you simply look at here in this negative feedback circuit and try to gauge whether I can have a problematic RL or a range of RL for which it will be fine or not. Right. Looking in impedance should be this R out should be much lesser than RL. Right. So if that is satisfied, we are good. Any other way of figuring out? When you are doing the looking in impedance, you'll have to go around the loop and do a calculation based on how the negative feedback works. And this is only one GM and with fairly simplistic resistive divider feedback network. But let's say you have multiple things in the network. So is there any other way of figuring it out? So what is the principle in which negative feedback is working? Or rather, if I ask you, what should stop, what would hinder this negative feedback operation? What should change in the negative, in this topology that will make this negative feedback work incorrectly or imperfectly? Pardon? RL cannot be. So what happens RL if RL is too small? It will load, right? So the current will load. I mean, RL will load the loop. So that effectively is saying that you are violating this condition, correct? So that is correct, but I want to go one step back in the sense that can you relate the operation, the desirable operation of a negative feedback loop with loop gain? What should loop gain be? Very high, very low for the loop to work properly? It should be very high, right? And the good thing about loop gain is it's an open loop thing, right? You don't have to go around the loop. You can break the loop and there is a definite input-output relation that you can, in an open loop manner, you can establish. And all you have to ensure is that the loop gain has to be much greater than 1. Loop gain is a unitless quantity. So that loop gain has to be much greater than 1 in order for the loop to work. Is that okay, or that's a problem in understanding? I want an answer. Okay, this means can be yes or no, both. I don't know. Okay, so let me assume that you understand. So, okay, let's say we go ahead and do this, right? So GH, this block. So what is V naught if GH is much greater than 1? 1 over H. And as long as 1 over H is realized using ratios, that's stable. So for this to materialize, I need to have loop gain to be much greater than 1. Right? So if loop gain is not much greater than 1, this will not hold. So the key thing about negative feedback is that negative feedback will work properly if the loop gain is much greater than 1. So if RL is very low, can you comment on loop gain? Let's say RL is much less than R naught and this parallel combination of KR. Then in order to figure out loop gain, you don't need the loop also, right? You have to break the loop to find the loop gain. So how do you find the loop gain? Right, you break the feedback path. So you break this path. In fact, you can break it anywhere in the loop in principle. But let's assume we are breaking in the feedback path. And I apply firstly, input is not necessary because loop gain is a property of the loop and not particular to the input. And you apply a test voltage here. And I have broken it here, right? And I have to check the voltage here. And let's say call it V return voltage. So what will be V return by V test? What will it be? Yeah, so good. So minus, there will be minus because there's a sign inversion, right? The V test has been applied to the negative terminal. So minus GM times R naught parallel KR parallel RL. So your loop gain L is this GM times R naught parallel KR parallel by K, correct? Yes, thank you. If RL is loading, right, which means RL is lesser than this parallel combination of R naught and KR, then this becomes GM RL by K, right? If RL loads. So naturally, you see that in this case, your loop gain gets compromised. So if the loop gain gets compromised and if this becomes close to unity, right? If L becomes close to unity, right? So then clearly you don't have any gain in the loop. So naturally, I mean, this condition will get violated, right? So you'll have a problem. Okay. So what does this relate to in terms of transistor level implementation? For this, let me just say that I am doing K equal to 1. That is, I am looking for a gain of 1, right? So I don't want this K factor to come because, I mean, you can apply the K factor later on for generalized cases, but let's do a specific case of 1 where the input and output are connected, right? I mean, for example, if K is equal to 1, in this case, this will connect to here, right, directly for K equal to 1. So let's do the K equal to 1 part. And if you have RL connected here, then naturally you will see that this stuff, this RL will directly load the differential amplifier. And in order to figure out how it is loading, if I have to figure out the loop gain looking at this circuit, what should I do? I have to break the feedback. And where is the feedback getting established? Where is the feedback getting established if I have to relate the circuit on the top and the bottom? Yeah, so this gate to drain connection of M2 is providing the feedback. So I'll have to break it here. So I break it here. And I incrementally ground the input and apply a test voltage here and find out what is the return voltage here. Okay, so what will be incrementally, what will be V return over V test? For this, you can model this diffamp as a Norton equivalent that we had done. And then you can quickly figure it out. What is the Norton's equivalent of this? The short circuit current is GM times VI or V test in this case. And the output impedance is RDS2 parallel RDS4. And you have RL connected here. Don't we need to open? What do you mean by open the current source? Okay, so this one, yeah, I'm doing incremental right now. Yeah, so obviously when you do the analysis, you have to open the current source. That's fine. So if you are finding it difficult to directly look into the circuit and figure out, then obviously when you are putting the incremental, you can remove the current source, right? That obviously you'll have to do. But I mean, now I am assuming that we are comfortable enough to understand that voltages become short and currents become open, and we don't have to explicitly show that. No, right? In this case, no, because I have a mirroring from here. Half GM/2 comes from here, half GM/2 goes from there. Because of that, it becomes GM, right? Okay, so in this case, the sign will be negative because I have applied the input at the other terminal. So it will be minus GM times V test and this. So this is also expressed, I mean, one of the common ways of symbolic representation of this is keep the GM as is. This is V test. This is RDS2, RDS4. Okay. So you get the same thing. You get the loop gain to be. So in this case, L is GM times RDS2 parallel RDS4 parallel RL. So if this becomes close to unity, your loop is not working. At least not working as per expectation. So what is the solution? You'll have to, for a given RL, you'll have to increase GM then. Right? If RL is much less than RDS2, RDS4, then obviously this will almost be equal to GM times RL. So in that case, the only way to increase loop gain is to increase GM. So which means you have to increase current, you burn more power, so on and so forth. And there is also some limit to the amount you can have on the GM, given that you have a definite power budget, in the sense that you cannot really burn your battery off to bias one differential amplifier. So there is a maximum GM that you can probably achieve. So the other solution that what people normally do, let me ask you this. So what do you think is an alternative to this? Let's say you cannot get more GM, you cannot, let's say you have hit a GM max because of some power budget or something. So what is the other possible solution that you can think of in order to, if you have to increase the loop gain? But if RL is dominating, it really doesn't matter, right? RL is given by your customer, let's say. I mean, for example, if you are using your music player, right? The load is kind of given. So typically those have 10 ohm, 20 ohm, 30 ohm loads, very small loads, very large loads rather in that case. So you cannot really tamper with that. So what else can you do? Exactly, right? So you have to ensure that RL does not load the GM. So you have to put something in between. Yeah, right? So one possible solution is to use a voltage buffer in between the RL and the GM. Correct? So one possible solution is to do this. So use a voltage buffer. What is a voltage buffer that we know? Simplest voltage buffer. Source follower. So this is RO, this is GM. Maybe you put a capacitor and RL. So, and you take this to be your V0. And you might want to also get rid of the capacitor if you are confident that that this transistor, let me call this M5, can supply the appropriate current to the RL. It will load M5, but if you size M5 accordingly, it can still provide the adequate current. And this becomes your V0. And how will you close the loop? V0 has to go to one of the terminals, either the plus terminal or the minus terminal of the GM, to close the loop. So where will you connect V0 to? Minus. Okay, now how do you figure? Yeah, so we do the same test, right? So let's assume that any part of the loop I yank up. Let's say I yank this up. Then this goes down. If this goes down, what happens to V0? Goes down. So which means whatever comes back is negating the disturbance that you have provided, which means this is in negative feedback. So this is fine. So now what is the loop gain? Let's assume this we call it V1. Let's assume, okay, you don't have to even assume. So now tell me what is the loop gain? Okay, good question. If you have to place this K minus 1, where will you place that? Tell me. Yeah, no, you mean from V1?
Yeah, from V1.
Will that help? Yeah, but what is the output that we want? We want V0. So you are saying that I have to do this, right? K minus 1 R, and then connect it. So this feedback will work, but will the V0 be equal to K times Vi? No, not exactly, right? So what you suggested, this is actually used in some places. So I'll come to that, right? So, but if we have to draw a parallel between whatever we were doing earlier and now, so this is what we want. Okay. So let's say we are doing unity gain feedback. That is, by unity gain feedback, it means I want gain of 1 from input to output. I can always scale up by K by putting this K minus this divide by K feedback network. But let's say we are doing this now. So what will be the loop gain? This is V test, this is V0. What will be the loop gain? So what will be V1 in terms of V test? Minus GM times V test times R0, right? Minus GM R0 V test. What will be V0 in terms of V1? This is one of the standard architectures. It will be approximately same as V1, right? It will be approximately same as V1. But however, if I have to be a bit more precise, so it becomes V1 times GM5 by 1 plus GM5 RL. As long as GM5 RL is GM times RL, right? Yeah. As long as GM5 RL is more than 1, right? So this approximately equals to V1. So this becomes minus, total becomes minus GM times R0 times GM5 times RL by 1 plus GM5 RL. So if you can ensure GM5 times RL is much greater than 1, then we know that this gain, not that gain. So between these two nodes is approximately equal to 1. Then you can put your resistive divider here and take the feedback from here. But you have to ensure that GM5 RL is more than 1. So that is done. Actually, in some of the products that we use, some high voltage products, this type of feedback is also used. But there will be some error because of this, because this term will not be exactly equal to 1. Okay. So this works, this is fine, but there is an issue with this architecture.
Configuration is due to the problem and we couldn't increase GM given the part.
Correct.
Then we came back to the same point where we have against that something.
Correct, but this, yeah, that yes, you are right. But the good thing about this architecture is this need not be very large, because let's assume you have not been able to make this this the gain of the second stage is not proportional to RL. Correct? So if let's say you haven't been able to make GM5 RL be much greater than 1, let's say you make it 1. So this term will go to half. Not so bad, right? But if if you directly connect RL to the first stage, then the gain directly goes with RL. Right. So there is a benefit to it. Okay. So now there is one particular issue with this architecture, and the issue is the following. The issue is that of swing limits. So let's say you are operating with a power supply, which is 3 volt. Okay. So what do you think is the max? And you assume that this GM is a differential amplifier, right? This GM is this GM. So what is the maximum voltage to which V1 can go? No, so let's say this is 3 volt, right? So V1 is this node. So what is the maximum that V1 can go? So which transistor will be in trouble if V1 increases? M4. M4, right? M5 is fine. M5 will be V1, if as long as V1 cannot go above 3 volt, that's for sure, because that is the maximum that is available. So M5 will never be in problem. So if V1 goes high, M4 will be in problem. M4 can go into triode because the VSD of the PMOS is getting crushed. Correct? So V1 max is 3 volt minus 1 overdrive of the PMOS transistor. Correct? So this max is 3 volt minus V overdrive of M4. So if that is the maximum V1 can go, what is the maximum at which V0 can go? So this will be naturally V1 max minus the VGS of M5. Because you have biased the VGS you have biased M5 for certain current I0. So let's assume V overdrive, you have to keep 100 millivolt. And typical VGS, even in modern devices, are of the order of 400 millivolt, 500 millivolt. And you have to keep, so this becomes 3 volt minus 0.1 volt minus VGS. VGS is again 0.4 volt plus 0.1 volt. So this can go up to at max 2.4 volt. Correct? So you are losing about 600 millivolt across the VDS of M5. Does that make sense? Is this obvious or it's not obvious? If it's not obvious, let's go back one more step. Are you okay with the fact that V1 max is 3 volt minus V overdrive of M4? So what will be the V0 max? You have to keep the VGS of V0, right? If you don't have the VGS of V0, M5 will not. I mean, if you don't keep the VGS of M5, V0 will not be whatever you want, right? Your M5 has to be biased. So V0 will be whatever V1 you have minus 1 VGS of M5. And what is VGS of M5? Is threshold voltage plus overdrive of M5. The threshold voltage of typical devices is about 400 millivolt. And you want overdrive is, let's say, 100 millivolt. So you basically start from V1 minus 500 millivolt. So that's what you get 2.4. Now, this essentially means that the VDS of M5 has to be it has to be at least 2.4 volt. Sorry, VDS of M5 has to be 600 millivolt, 3 volt minus 2.4 volt. So you are losing that 600 millivolt of headroom. Now, on a supply of 3 volt, you are losing 600 millivolt. That is what? You are losing 20% of the available swing. And that 20% of the available swing, not only you are losing, but you will have to, you are burning power. And that essentially means that you are burning that extra power just to keep the transistor operating. There is no signal you are getting from there. That room of 600 millivolt is going in order to just bias the transistor. No signal is using that headroom. So that is one of the reasons these type of architectures are not very common in low voltage supplies. At 3 volt, this might not feel too much of a problem, but modern devices work in 1 volt, 1.2 volt, that much power supplies, even sub 1 volt. But this threshold voltage hasn't really scaled. Threshold voltage have remained around 300 millivolt, 400 millivolt. So if you lose like 500 millivolt from 1 volt supply, then you're gone, right? So you are essentially burning power without having any signal. So this type of architectures have started to become less and less popular in low voltage supplies, but these are one of the very popular architectures which are used. Even if you are, when you use in ES201, you have used 741 op amps. So the output stage of the 741 op amp is a source follower, right? A slightly different source follower, but it's a source follower nonetheless. But your 741 works at very high supplies. It can go to plus minus 10 volts, right? So it's not too much of a problem. But when you use custom design with low voltage supplies, this is something that you see less and less of. So the obvious solution is we have to select an output stage where I don't lose so much of headroom just because I have to bias it. Correct? And why am I losing so much of headroom is because I have to keep this VGS. Correct? So is it possible? The question is it possible to select an output stage where I don't have to keep this VGS drop between the first stage and the second stage? NMOS will simply not do. That is evident, right? If I keep an NMOS, I have to keep that VGS. I have to allow that VGS. If I cannot use an NMOS, what else can I do? Use a PMOS, right? So let's use a PMOS. So what is the good thing about a PMOS? If I use it at the output stage, this will become evident right away. So still my V1 max can be 3 volt minus 1 overdrive. So this can be 2.9 volt. So what is V0 max while keeping M5 in saturation? Pardon? I couldn't hear. Okay, but which is the source? It is a PMOS. The source is on top. So this will be. Can you repeat your answer? I probably didn't catch you. Why plus threshold voltage? Okay. Correct. Yes. Yeah. The threshold voltage of the. Yeah. Pardon? Okay. So if you use this PMOS, then you have to give this VGS allowance, right? So this has to be at least some 500 millivolt. But in this case, if you use an NMOS, the VGS allowance goes here. Goes on the other side, right? But what can V0 go? V0 can go higher than V1, right? Or in other words, if you want to see from the source side, you'll have to keep 1 overdrive between the source and the drain. So this exactly, right? In the PMOS, the source is at a higher potential. Yes. So this can go to as high as 2.9 volt. Right? In fact, not 2.9. Yeah, it can. So from here, so let me express it in this manner. So if this Vmax is 2.9 and VTP is 400, so this looks like this can go up to 3.3 volt from this relation between V1 and V0. However, I know that V0 cannot go over VDD, right? I have to keep at least one threshold, one V overdrive between the source and the drain. So from this relation, I know that V0 will be at max 2.9 volt. Correct? So this is greater than VDD. So obviously you cannot go better than VDD. The other limit will needs to be satisfied. So V0 max can be 2.9 volt. Pardon? Okay, if it's 3 volt, then the VSD is 0, right? VSD is 0, which means your transistor is in linear region. So now the good thing about this architecture now with respect to the other one is quite obvious in the sense that now you are losing only 100 millivolt because of the biasing requirement, not 600 millivolts. Okay, so as the supply scales down, this becomes a far more lucrative architecture than with respect to the other one. Yes. Pardon? It's VSD. Source to drain. Source to drain will go to 0, right? Okay, so are you convinced that this is a better architecture with respect to the previous one? Okay, fine, good. But now there is a problem. And the problem is as follows. Here your E250 knowledge will kick in. So something that we have been avoiding till now is a role of capacitances in analog circuits, right? So your transistor, what is your transistor? Your transistor is nothing but a metal oxide semiconductor, and there is a capacitance between because of that oxide, right? So if it's an NMOS, this is P minus. So there is channel charge here. So there is a capacitance between the channel and the gate. Now, what we normally do, for circuit designers, we try to project these capacitances between the terminals, because there will be capacitances between all sorts of between all points of the devices, but they are inconsequential as long as we cannot if we cannot express its effect in terms of its if we cannot project their effect on the terminal boundaries. So what we generally do is we say that these capacitances are distributed all over the place. But what we will say is that since we distributed capacitance is difficult to deal with, we'll split the capacitance into two parts, one that is towards the source, one that is towards the drain. We club the capacitances together in such a way that they are referred between the gate and the source and gate and the drain. Okay, so essentially we'll say there is a capacitance between these, and we'll assume that these don't exist. So this becomes CGS and this becomes CGD. Similarly, there will be a capacitance between the drain and the bulk. So there will be capacitance between the drain and the bulk. We call this CDB. So similarly, there will be capacitance between the source and the bulk, called CSB. Okay. So your transistor model now has this capacitance, this capacitance, this capacitance. So this is drain, source, gate. Yeah, they are there. We have not been using them just because we have been doing all quiescent and small signal, low frequency stuff. At low frequencies, capacitances are as good as open, right? So we have been avoiding them, but you will see we cannot avoid them for too long. These exist, these are part of the devices. So this is CGS, this is CGD, this is CDB, this CSB. So your incremental model of a transistor now becomes this in case of an NMOS. Similarly, we'll have in case of a PMOS also. So this is the body. And on top of that, now the stuff that we have added. Okay. So this becomes your full transistor model. However, I mean, we'll have to simplify. This is not something that we can readily appreciate by looking at it, how it will behave. So we have to simplify. So that simplification is case by case basis. For example, in case of a common source amplifier, your source goes to ground, right? It is a grounded source. If source goes to ground in a CS amplifier, if your source goes to ground, then we can simplify this as there is a capacitance to ground. This becomes CGS. GMB goes off because VBS is 0. CSB also goes off because source and bulk are grounded. CDB will be there. And there will be CGD. So CGS and CDB are okay because any grounded capacitance is easy to deal, right? So one terminal is fixed. It basically comes in parallel to whatever is connected to the terminal. So that's easy to deal. The problem comes because of CGD. And we'll see how to deal with the CGD without writing too many equations. We'll see that in the next class. But the key thing that I want to focus here is the following. The effect is what? The effect of this capacitance is this GM, however you have realized it, doesn't really matter. It's a differential amplifier or a common source amplifier. This GM will have a capacitance at this node. RO. Let me call this CO, or let me call this C1. This C1 is probably a combination capacitance of whatever is connected to that node, right? So let's assume that is C1. And now you have okay, by the way, one very important thing I forgot to mention. So let me go back one more step. So in this case, in this diagram, where will you connect the V0 to? The plus terminal or the minus terminal of the GM? Okay, let's connect it to the minus terminal of the GM. How will you test? You do the same thing, right? So let's say this increases. If this increases, what happens to V1? V1 decreases. If V1 decreases, what happens to V0? No, it will increase, right? So there is an inversion that has happened because you have put this common source. This is essentially a common source stage, right? The second stage is the common source stage with the PMOS input. So because you have a second common source stage, you have inversion. So naturally, if minus is not the terminal, plus becomes the terminal. Okay. A version of this was there in the quiz with an NMOS second stage, if you recall. Okay, so in this case, this will go here. And you will have a capacitance at this node. This is C2. So now what happens to the loop gain? What do you do again to figure out loop gain? Yeah, so break the loop, round it, V-test, and I have to figure out V-return.
So C1 figure from the new
New device capacitances I have clubbed in together, right? So how we'll see how this C1 and C2 relate to CGS, CGD, we'll see. But let's assume that they are there because we cannot avoid them. So if they are there, so what will be V1? Yeah, it should be GM times V test is the current that flows into a parallel combination of R0 and C. So it's better to go into conductance domain because they add up, right? Conductances add up since they're in parallel. So this becomes G0 plus SC1. Okay. What about V0 in terms of V1? You can assume the M5 to be an ideal GM. So what will be the incremental current through M5 because of V1? GM5 times V1, right? Which direction? Upwards, right? So this current will be GM5 times V1 flowing upwards. So what will be the voltage at V0? Minus GM5 V1 by GL plus SC2. So what is V return in terms of V test? Becomes multiplication of these two. So it becomes minus GM times GM5 times V test. Which means your loop gain now is a function of S. Is okay. The most popular way of writing this is separating the gain, DC gain, from isolating the DC gain and having the rest of the stuff together. So basically you take G0 and GL from the denominator and club them on the top. So this becomes GM by G0 times GM5 by GL. And this is again referred to as A0 by 1 plus S by P1, 1 plus S by P2, where A0 is referred to as the DC gain because at zero frequency, when you set S to 0, your L of 0 is A0. So that's called the DC gain. So A0 is DC gain or gain at DC frequencies. And what do you refer to P1 and P2 as? Poles, right? So this has two poles. So poles at minus P1 and minus P2. Okay. Where in this case, P1 is, this is equal to minus G0 by C1, and this is minus GL by C2, I think, right? Yeah, C2. Okay, these are real poles, not complex poles. These are real poles of the loop gain. So what do you think is following next? We'll do it in next class, right? Okay, thank you.